All right, so this video is going to be a continuation of looking at whether or not differential equations were separable. Now we're going to take the ones that were separable and we're going to solve them. So for these notes, we are solving separable differential equations. And there's a few steps we have to go through. So first step is to separate the differential equation. Second step is to integrate. So when we separate the differential equation, we have something with y times dy equals something with x times dx. And so to get rid of the dy and the dx, we're going to integrate each side. And since we're integrating and it's an indefinite integral, that means we're going to make sure we put the plus c on the end. The third step after that is to solve for y. And that's if possible. Typically it will be. And then the fourth step is to use the initial value to solve for c if they gave you an initial value. So if there was an initial value, solve for c. All right, so just a little reminder about differential equations. Differential equations can be represented by slope fields, and a slope field shows an entire family of functions that are solutions for that differential equation. So when we separate the differential equation and integrate it and solve it, we are finding, when it has the plus c in it, we are finding the equations that represent that family of functions. So all the different equations that would go with that slope field. When we solve for the plus c, then we're solving for the specific equation that is a solution to that differential equation. So I just wanted to remind you guys that solutions for differential equations are not points, they're entire families of functions, or more specifically, one specific function. Okay? All right, so we're going to go through some examples. We're going to say y prime equals x times y. So remember, if it's going to be separable, then the part that's in terms of x and the part that's in terms of y have to be multiplied together, which is what we see here. So I'm going to go ahead and rewrite this problem as dy dx equals xy. So I want everything with the y on one side and everything with the x on the other side. So I'm going to go ahead and divide the y over. That gives me 1 over y dy equals x dx. And so I've done step 1. Now I can go ahead and do step 2. So I'm going to integrate each side. So if I integrate 1 over y, then I get ln of y plus c. If I integrate x, I get 1/2 x squared plus c. And now these plus c's they could be the same, they could be different, they just represent a constant. You don't need to show you have a constant on each side, because as we solve for y, we would have moved it to one side anyway. So most people don't put this plus c, they just put 1 over here and they say that represents the constants for both sides. So we're going to go ahead and do that from now on. We'll just say leave the plus c on the right side. And then I'm going to go ahead and solve for y. So to undo ln, I'm going to e both sides. So that means y equals e to the 1/2 x squared plus c. And if you guys recall, the way that exponents work is if you have exponents that are added together, it's because you had two bases that were the same that were multiplied together. So this resulted in this. So I'm just kind of undoing that process. Now e to a constant is still going to be a constant, because remember, a constant is just a plain number. So e to any number still represents a number. And so the way that we write this is we're going to call this a constant, and we always move that constant to the front like a coefficient. So we're going to say CE to the 1/2 x squared. And that is going to represent our family of functions. So they didn't give us a point. We can't find the specific function, but we know that this is what the slope field would be of. And then we could use a specific value to find something that's more unique. All right, example 2. So here we're going to have dy dx equals x squared over y squared. And this goes through the point 0, 2. So it is separable because I can see the two terms, they're divided, but I could easily think of it as multiplication. So I'm going to go ahead and move the y's to one side and leave the x's on the other side. And now I'll go ahead and integrate. So I have 1/3 y to the third equals 1/3 x to the third plus c. And now my goal is to solve for y, and since I have an initial value, at some point I'm going to plug the 0 in for x and the 2 in for y so I can solve for c. Now when I learned how to do this, I solved for c at the very end, but you, at any point now, we can solve for c. So whenever you feel like you're ready to plug it in, that's totally fine. So I'm going to go ahead and start solving for y, so I'm going to multiply by 3 on this side, and that means I'm going to multiply by 3 on this side as well. So I have y to the third equals 3 times 1/3, which is just 1. 3 times 1/3, x to the third plus 3c. 3 times a constant is still a constant, so I'm just going to keep calling that c. All right, so now I can go ahead and cube root each side. So I have y equals the cube root of x to the third plus c. And now I can go ahead and plug in the 0 and the 2. All right, so I'm going to go ahead and plug in the point now. So if I plug 0 in for x, then I get 2 for y. So the cube root of c equals 2, and if I cube each side, then I get c equals 8. So that means that my function is the cube root of x to the third plus 8. All right, example 3. dy dx equals 6x over 2y plus cos y. So it is separable. I'm going to go ahead and multiply the y's to the left side. So 2y plus cos y dy equals 6x dx. And so we're going to integrate each side. So 2y, that would be y squared plus sine y. And then this one would be 3x squared plus c. And in this case, we can't solve for y. We don't know how to do that. And so I'm just going to leave this equation like this and call it good. All right, the fourth example, we're going to say dy dx equals x over square root y. That was one of the ones on your sheet of whether or not they were separable. So we're going to multiply the square root of y over here. So square root of y dy equals x dx. And I'm going to go ahead and write this so it has an exponent, just because that'll be easier for me to kind of think through. And I'll integrate each side. So if I add 1 and divide by 3/2, that gives me 2/3 y to the 3/2 equals 1/2 x squared plus c. And so I'm going to multiply both sides by 3 over 2. So I have y to the 3/2 equals 3/4 x squared plus 3/2 multiplied by c, it's still a constant. And then I'm going to go ahead and I'm going to take the y and raise it to the 2/3 power. And so I'm going to take this and raise this to the 2/3 power. And so my family of functions is 3/4 x squared plus c, all raised to the 2/3 power. Okay. And then last one, we're going to do y prime equals 1 minus 2y through the point 0, 2. And I just wanted to clarify for this initial condition, I've happened to give you 2 points, they were the same, as examples where the initial condition happened to be a y-intercept, and that can, I mean, I'd say that's pretty common. However, it's possible for them to give you an initial condition that is not the y-intercept of the function. It could be something else. So just keep that in mind. Okay, so I'm going to go ahead and write this as dy dx. And if you notice, there's nothing that has an x in it. So what I'm going to do is I'm going to think of this as like that times 1, and I'm going to leave this on the x side. So there's no x's in here, but it's okay because we'll actually be able to integrate it. So you'll see that in a second. I'm going to have 1 over 1 minus 2y dy equals 1 dx. Okay, so now I'm going to go ahead and integrate each side. On this side, I have, it's kind of like, oh, if I was to take the derivative, that would be a chain rule problem, which means that when we integrate it, it's actually a u substitution problem, which I know that we're a little bit rusty on, but we'll get back to that in the next unit. So here, the u would be 1 minus 2y, and the derivative of u would be negative 2 dy, which I don't see hanging out in the problem, so I'm going to divide it over. So I have negative 1/2 du equals dy. So the problem I'm doing is negative 1/2 times the integral of 1 over u du. And over here I could go ahead and integrate that side. That's just x plus c. So I have negative 1/2 ln of u equals x plus c. And I can go ahead and replace the u with 1 minus 2y. And then I'll go ahead and multiply each side by negative 2. So I have the absolute value of 1 minus 2y equals negative 2x. Negative 2 multiplied by c is still just a positive c. Oh, I missed my ln. That's why something looked weird. Okay, so now I'm going to go ahead and take the e of each side to get rid of that ln. And so what that leaves me with is I have 1 minus 2y equals e to the negative 2x times e to the c. So remember, anytime we have two exponents that were added together, we just split them apart and write them separately. And remember, this is a constant, so I'm going to put that in the front. So I have 1 minus 2y equals c e to the negative 2x. I'm going to subtract the 1 over. And then I'm going to go ahead and divide by negative 2. So c divided by negative 2 is still a constant. Negative 1 divided by negative 2 is now a positive 1/2. So here's my family of functions, but now I have that it goes through the point 0, 2. So I'm going to say 2 equals c e to the negative 2 times 0 plus 1/2. And so I can go ahead and subtract that 1/2 over 3/2 equals c. Anything to the 0 power is just 1. So 3/2 equals e times 1. So c equals 3/2. So I'm going to say y equals 3/2 e to the negative 2x plus 1/2. And that is my specific solution.